Okay guys, so here we are with another live stream, and I know that I'm not doing too many live streams because I'm gonna be honest with you guys, I'm not very comfortable speaking in English, and especially in a live stream. I mean, I'm not comfortable in my videos where I have a script, imagine in a live stream. But I had this idea because I have a lot of questions. Anytime that I design a PCB, I got a question for how do you expose the tracks, how do you make that kind of tracks, how to make the PCB with this shape, how to order then the PCB if it has multiple parts, and so on. So I thought it would be nice to just start and make a PCB, start to finish, make the schematic, talk about how to make the schematic, how to have an idea, and then pass that schematic to a PCB design, how to design the board, how to select the thickness of each track. I'll show some tips and tricks and some very basic design rules, and then we'll just make the PCB. And also have in mind, we'll be focusing later in the video about this PCB. This is the PCB that I will be using. By the way, I'm not sure if the audio, let me just check if the audio is correct here, because I want to make sure. Yes, I think we have a good audio. And also let me just make a post on Instagram because I'll share the link there, so maybe more people will just come in. So the post is now done and we can continue with our video. And by the way, I'll be also reading the comments, not all the comments but some comments. Thank you very much. If you think my English is okay, I know that I'm improving it. Actually, if you go to my first videos, I'm not sure if I should say this. Anyway, if you go to my first videos, you will see that I was just making some sort of accent and just making like a character because I wasn't comfortable with my own English, but then I just changed it. I've changed a few words. I just got improved. I just made a lot of improvements, and now I have this. This is my English, and I hope that you like it. Anyway, let's just see. Okay, so what I was saying. We'll just make a schematic start to finish, and I will show some tricks and some basic design rule checks, and then you will just ask me questions in the comment section, on the chat, on live stream, and I will just show that directly here, because like that we can solve a lot of questions and problems. So let's just start. We'll be focusing on this PCB, but that will be a little bit later, because first we'll go over some very simple PCBs, because I don't want to start directly with this complicated PCB. As you can see, we have a lot of components and it's huge. By the way, we'll have this project on Sunday, and I don't want to make you a spoiler, but you should go and see it when it will be posted, because this is awesome. This is one of my most dangerous and also very complicated project that I've made, because this works with 380 volts, which is very dangerous. But anyway, so we'll just start with some simple PCBs, we make a schematic, and then we pass to some more complicated PCBs, and then finally we make this one, but we won't make it entirely. I'll just show you some tips and tricks how to make some tracks, and then we pass to the already made schematic, which is this one here. Let me just change to the desktop view. This will be the schematic, because I don't want to stay here like 3 or 4 hours. When I've designed this PCB, I spent like 4 hours entirely, and only to make the tracks, I think I spent like 2 hours. So you don't want to stay here and see me how to route all these tracks in 2 hours. So what I will do is just, for example, show you how to make the small tracks for signal, how to make the power tracks, how to expose the copper, how to change the angle of the tracks, and so on. Some basic placement of the components and the tracks, and then we jump directly to the final schematic, because otherwise we will be staying here for hours. So first of all, we will talk about the schematic and some basic rules for the schematic as well. You want to have a schematic very well organized. As you can see here, I'm trying to place each part in a box, and also I'm using a lot of these connectors to show what I want to do with these connectors. For example, this is a connector, this is a symbol, and this is a net port. The idea of using net ports is to just not make lines all over your schematic. I have an example here. This is a schematic that I've actually downloaded for one of my projects that was about the Nintendo based on Arduino. And as you can see, it's a good schematic, but it's very difficult to follow. First of all, the pins name are doubled and overlapped, and you don't even know if this one is the IO26 or this other one or the bottom one, because the name is overlapped. And at the same time, if you want to just follow a track, for example this one here, if you want to see where it was connected, you just follow it like this with your with your mouse, and when you get here, I'm not even sure if it was this one and this one, because I already got lost. Imagine here where you have like, I don't know, 10 tracks. So never do this. I mean, it's a good schematic, but as you can see, it's very difficult to follow, and that's why we use the net ports or the symbols. So the platform that I'm using for this tutorial, is EasyEDA. So just go to easyeda.com, you make an account and so on. And I'm using this because it's free, so anyone could use it. But also this will be the same, exactly the same for Design Spark, Altium, or any CAD software or SPI software that you are using. So as I was telling you, you have to use the symbols or the pads. Let's just go over the symbols. First, we have, for example, the ground symbol and the 12 volts one. You just go to the commonly library, and as you can see, you have the ground and VCC. So let's just get this VCC here. You place it on your schematic, and if you want to change the name, just double click the text and just call it 3.3 volts, for example. Imagine that you are making a 3.3 volts connection and you want to connect it to any other part of the schematic. Instead of just placing a line like this, for example, you want to connect it here, this is very ugly, and actually it's overlapping a lot of other parts of the schematic. So you don't want that. Instead of doing that, you just name it this 3.3, you click it, you copy it, you paste it where you want to have the connection, and just make a connection like this. So that basically is a virtual connection between this 3.3 volts and this 3.3 volts. And that will go, so, but if you change the name here to 3.3 volts and instead of V, just VO, have in mind that this is not the same as this one, because the connection is made with the name, so they have to have the same name. So let me just delete this here and this here and show some real examples. For example, these are all ground, and as you can see, I'm using different grounds because sometimes you have circuits that are a little bit more complicated that will have double grounds, because you have to separate the high voltage ground or the AC ground from the other ground. In this case, I was just adding a shunt. I'm not sure if you can see it here. Are these two components, and these shunts are basically some very small resistors that with maybe values of 10 milliohms, and you want to use these shunts to measure the voltage across them, and by dividing it by the resistance, you get the current value. So the ground of the 380 volts should not be the same as the ground that is connected then to the IGBTs, which is this ground here, because that would mean, if I were using the same name here, ground and ground, it will mean that I will have a short circuit between these lines, and you can measure a voltage drop between a short circuit. You have to have an open circuit and measure it across the resistance. That's why I'm using two different symbols. And by the way, when you place a new symbol, let's just place it here and give it again 3.3 volts. Oh no, let's just give it 7 volts to be different. And as you can see, it will also create a net for me. And if we go here to Design Manager, we go to Nets, we refresh, and as you can see, I have a 7 volts connection, and the software already tells me that there is an error with this. And basically, there is nothing connected to it. But if I take this 7 volts and maybe connect it here, let's just say that I want to connect 7 volts here, I save it and refresh once again. As you can see, the error disappeared and we have the 7 volts net here. And anytime that you click it, it will take you, depending on your schematic, when you click it, it will take you there where the connection is. And if I delete it and refresh once again, the 7 volts connection just disappeared. And that's how you can use symbols. The other thing that you could use to make it very well organized are the net ports. So get here in the menu, and you have this net port here. You click it. Once again, you drop it on your schematic and give it a name. Let's just call it output. Okay, so this will be an output for anything. So let's just say that you want to connect this point. No, let's just say this point here, the other point that we have before. Let's just say that this is some sort of output. You want to connect it to your driver. Instead of just making a line like this directly to the driver, let's just connect it here. Look how ugly it is. And then it will create another problem, this dot here, and we'll talk about that in just a moment. Instead of doing just that, you can just copy this with the same name. You can press R to rotate it in any direction. You place it wherever you want on your schematic, and then you make the connection to your pin, for example, here. And now as you can see, this point is connected to this point and you don't have to pass a lot of wires. And when you have this many components and this many connections, you want to keep it organized, because even if it's a schematic for you, imagine that in the future you'll be an engineer and you want to pass that schematic to anyone so they should understand it. So it's very important to keep it organized. And that's how you do it, with symbols and with net ports. Obviously we have more symbols here. We can use this one if you want. You can also change the name to this one. You can use the, I think this one is for giving a net label, so you just place it on the net and then you just change the name of that, let's just call it IO, and then this entire net will be called IO. So I'm not really recommending this because I want to leave the software to give the name to the net however it wants, and I only want to change the name of the connection. So everything understood till now? You want to keep it organized, and also, for example, I use these boxes to separate the parts of the circuit. When you have a circuit, you will see that basically any circuit will have some sort of input. Otherwise, it's not an electrical circuit. If it would be a battery, it could be a power supply, it will be the main input voltage with a regulator and so on. So I want to separate that. For example, this is the main input of the battery, which basically will be these 2 points here. I'm not sure if you can see on the webcam, but this will be 2 connectors for the battery. And then I pass it to a connector here, which will be a switch, and like that we can turn it on and on. And then this VCC is connected directly to my regulators. And then the regulators will be here because this PCB will have different values. It will have 380 volts AC, 380 volts DC, 18 volts AC. We pass it to a rectifier to 18 volts DC. We use a voltage regulator for 12 volts. Actually, this is a regulator for 15 volts, so I should change this. Actually, I will do later because this is an already made schematic and I don't want to mess it. But anyway, we have a regulator for 15 volts and then for 5 volts. And these are connected to the rest of the circuit. For example, if you want to connect the 12 volts, regulated 12 volts to your driver, just place that icon here, make the net, and you have it connected. And that's it. Actually, I've made an error here. I'll just remove it, and I don't want to make any errors because this is an already made schematic. And I'll share with you guys the schematic this weekend when I will be posting the project of this PCB. And then I'll just close it into a box like this. You can just take this box tool. As you can see, you can draw boxes. And inside, you can just take the text tool like this, double click it and give it any name that you want. You can name it part 1. I don't know. Any name that you want. You can just change the size. If this block is more important than others, you can just change the size and so on. This is something that I do. Not all the engineers are doing this. This is something for me because like this I can orient it a little bit better in the schematic. I know this will be the IGBT part. This will be the battery input. We have some peripherals like the voltage feedback and the fan control. This is the driver for the high frequency, high voltage transformer, which is this one here. So like that you keep the project organized. And by the way, very important, when you start a project, give it a name so the people should know what project are you working on. And also you can give it a version. For example, this is version 1, but if you're doing version 2, 3, you can change it here so you could keep it organized for you as well, because you have different changes but different versions of the same schematic, and like that you can see where you've made that change. You can enter your name and the date, and basically that will be a well organized schematic. So now we'll start our own schematic and I will show step by step how to make one, and we'll do it with a very simple project. So what I will do, I'll just go to my website and search for a project that is using a PCB. For example, we can use this one, but this is very simple, just a few resistors. Let me just see here. The audio amplifier has a PCB, but that's very, very complicated. Actually, I've seen here this one. This was very recent. This is the 433 megahertz control, and I think I'll just use this one as an example. We have the transmitter and the receiver, and the transmitter, let's just start with the receiver because it has a very interesting part, because the receiver has this part here, the AC to DC transformer, which is a component that you can find in EasyEDA, and you'll have to make it from scratch. And I also want to show you how to create components. Imagine that you are designing a PCB and you don't find exactly the component that you want, and you have to design it yourself. You open the data sheet, you see the sizes, the pad size, the pad orientation, and so on. So we'll have to design it, and we'll go over that as well. So just open this in a new page, and I have a double screen. So what I'll do, I will take this page here and pass it to my other screen, because like that it will be a lot easier for me. We go to EasyEDA and just start a new project. So we go to new project, let's just call it 433 megahertz live example. Obviously this is just a name for me for this video, but you should give it a very serious name related to your project, and also description. For example, it could be something like, this is a project related to radio frequency connection, controlling a light using an SSR, etc. You can place the description here. We click save, and that will automatically create for us an empty schematic. Let's just wait. It's not creating a schematic. Why not? Why is this not creating a schematic? I did something wrong. New project, 433 megahertz live example, and save. Already exists. This is very strange. Live example. Let me just delete this. I can find the delete button. Delete. This will open a project. Anyway, it will already create a schematic for you. New project, 433 megahertz. Sorry, this is a bad example. Bad example. Bad example. Save it, and this should. There you go. This should already create a schematic for you, and you can just click it save. And as you can see, you have the project here. 433 bad example, and you also have the schematic, which is called sheet, but you can change the name to any name that you want just by double click it or modify. So this is our schematic. Obviously the first step, just give it a name. Let's just call it 433 megahertz transmitter receiver RX. Let's just place our name, Electronoobs. You can leave the EasyEDA logo if you want, but if you maybe share this with another engineer or so, you maybe want to just delete this icon. The date will be this one, and it's the first. Actually, this is the second one because I've already made the first one. So we just make the revision here, and we start placing our components. But before we do that, let me just check the comment section, because I'm pretty sure that you left a lot of messages. Let me just read a few ones, and if you have any questions, just leave it in the chat box, and I'll try to answer a few of those questions. We have time, don't worry. Let me just check the audio here. Okay, the audio is quite good. Okay, so let me just see. Welcome. Let's just see what other questions we have. The audio is perfect, thank you. Just don't use "I'll be back" and you're fine. What do you mean about that? The "I'll be back" like Terminator or what? Your old videos are fine too. I mean, I know that the video content is okay. I was talking about my accent. I was making a forced accent just to cover my bad accent. I was making a character. That's what I was saying. I was sounding like Russian. "What's up, my friends? Welcome back." And stuff like that. And then I just improve it and just get rid of that accent. And this is how I speak English right now. I'm not forcing to make any kind of accent. Okay, what kind of software are you using for PCB design? Usually I use this one, it's EDA, but I'm also using Altium. By the way, you have a free 1 month free, I think, for students if you want. And Design Spark. I've been using Design Spark for like 5 years, but that's a little bit old. Anyway, right now I'm using EasyEDA, and the best part of EasyEDA is the library. If you click it here, you can see that you have the symbols for some of the components from LCSC, which is a company that is selling the components, and you can see you can buy it directly. You have this icon here, you can buy the component, but the best part is the user contributed. So let's just put a buck converter without the M, buck converter. So This will be the parts of buck converter that you can find on LCSC, but then you get the user contributed, and these are all the parts that other users designed and shared with you. So if you have a small buck converter that is sold on AliExpress, let's just go to AliExpress, for example, to buck converter. For example, this very small buck converter here. I'm pretty sure that you won't find a symbol schematic on LCSC for this buck converter, but someone designed the schematic for this one and shared it with us. So you go to EasyEDA, and in user contributed, you just scroll them. Look, I think this is the same. I'm not sure if this is the same. No, this has only 2 pads, but if you spend a few minutes here, I'm pretty sure that you will find, I think this one is. Yes, 2 pads here and 2 pads here, might be this one. You only have to check the size so you can place it here. But actually, if you click the symbol here, you go into the symbol, you get the measure tool, you click here and here, and like that you will have the size. This is 70 millimeters, so I'm pretty sure this is not the one that we are looking here because this is very small. But then you go into the size of the product, which I think is this one here. Yes, 17. I think this is the one then. It might be this one. Anyway, so that's the good part about EasyEDA, because you can find a lot of components that are not by stock, by default on the library of LCSC or any other SparkFun or so and so on, any other company that is selling components, because are already made modules, and you can find those in here in user contributed. That's one of the parts that I like about EasyEDA. Okay, let's go to the other questions. Hello, sir. The RTC and LCD I2C directly connected them in SDA and SCL. There is no code for SD module. I don't know what you are talking about. I think you're talking about other project, but so many projects are using a nice crazy communication with SDA and SCL, so I don't know what you're talking about. I'm in school, please lesson now, ha. Love your videos, thank you. Short circuits are good, a lot of flame. That depends. If you want to make a good project, short circuits are not that good. I've jumped a question here. The music is distracting. I don't have the music. I have the music. Oh, sorry, I have the music activated. Why? Sorry for that. It's just my OBS got crazy. Sorry about the music. And it's like we've been live for like what, 20 minutes right now, and I just stopped the music. And actually I had the music background on loop, so even if it finished, it will repeat itself. Anyway, let's just see any more question here. Is the live recorded so we can revise if you forgot something? Yes, this video is live right now. So you can ask any question right now if you want, and I will just try to answer it. Okay, please make a tutorial about Ultimate Designer. I am preparing that, but Ultimate Designer is not free for anyone, so the public is not that interesting. I'm preparing another tutorial about Ultimate Designer, but it should be the same as this one, maybe a little bit different, because they are both PCB designing software, so stay tuned for that. Make a high voltage BLDC motor controller. I've already made that. You mean a VFD controller? Or, I mean, a brushless motor, but what is high voltage for you? I think I've made one with 48 volts, and more than that, 100 volts. Can you increase the audio level a little bit? Of course I can. And the microphone is this one. And I hope that I won't jinx it. Properties. And the microphone. Where is the microphone? I think my microphone right now is at its maximum level. And I can hear myself very well. Oh, okay. Someone asked if I will upload this video to my channel. Yes, this will be automatically uploaded to my channel. So if you want to see it like 1 hour from now or maybe tomorrow, you can just get to my channel and you will see it. But if you want to place a question, you have to do it now. Okay. Yes, my video will stay on YouTube. Okay, so we can continue. We have our design, our schematic open. We have our PCB that we want to design, which is this one here. I will open a new image and just pass it on my other screen because it's easier for me. And we can start designing. So we add our parts. The first part that I like to start with is the voltage regulation part, because that will be the input of our PCB. I know that my PCB will work with 12 volts. I'm not sure if I can show you here. Yes, it will work with 12 volts. This is a very small cell battery, and I know that usually these are 1.5 volts, but trust me, this is 12 volts. So I'll just grab my commonly used icons of VCC and call this 12 volts. So I'll know that this will be my input. And then I'll want to regulate this 12 volts to 5 volts because this is using the ATtiny. This is a microcontroller and this works at 5 volts. So for that, I just go to library, and I know that the regulator that I want to use is the AMS1117. Just put AMS1117. We go to LCSC or GLC PCB assembled, and this is not the one I want, the 5 volts one. I want the AMS1117 5 volts, which is this one here. We click place, and just like that we have our first component. So we also grab a ground icon, we place it here, and this PCB will have only one type of ground, which will be this one. We use the wire tool to just add a connection between the ground of the component and our ground, and the V-in will be 12 volts. V-in will be 12 volts. As you can see, the name of this component is quite big. If you don't want to show the entire name, just place 1117, and like that it will be okay, or AMS1117, and like that we have our component supplied. And now we have to make another output, another icon for the output. The 12 volts is the input. We copy this and we paste it and change this to 5 volts because this is regulated. And then we place it here. By the way, when you are designing, let me just check here to see if you, when you are designing a PCB, I always have with me a caliper like this one, because there are some components that on the designer will appear with a size, but then in reality they have a different size. For example, the battery, there is no component on EasyEDA or any other design that will have the exact size of the battery from here and to here. So what I will do, I will just add 2 pads, this one and this one, and then when I design the PCB, I measure the battery with a caliper and just place the exact same distance between the pads. Or for example, maybe this coil is a coil that you wind it yourself, so you won't have a stock symbol or PCB layout for your PCB. So instead of doing that, you just place 2 pads like this one, and then you measure it with your caliper and place that distance on your design. So have in mind that having a caliper with you is very useful. For example, when I was designing this PCB, we'll go over this as well, I didn't find the exact shape for the transformer, which is this one here, this square one. Okay, this one here. And that transformer was based on this module here. So what I've made was to get this transformer out, measure the distance between the pins, measure the distance between the vertical alignment, the sides of the transformer, and I've made my own component using the caliper and then using EasyEDA. We'll go over that in a moment. So now we have our component supplied. The only problem is that it doesn't have any sort of decoupling capacitor. So what I will do is to add a capacitor of 10 microfarads, because I know the linear regulator is very stable, but if you don't want noise, you have to add some decoupling capacitors. And I think this will be a 08005, sorry, is a type of size, SMD. Let's just look to SMD resistor sizes. And if we open, like for example, this one, now, okay. So as you can see, we have 0402, which is very common, but very small, 0603 and 0805. If you look on my PCB, this is, for example, a 0805, but this one is a 0603. And smaller than this one, it will be, this one is a 0603. Smaller than this one, it will be the 0402, but that will be very difficult to solder using your hand. Maybe if you're using solder paste, I mean, I can, but I know that a lot of people won't be able to solder it because it's very, very small. For example, let me just search here for multimeter. This multimeter here was using 0402 resistors. I'm not sure if I have a picture. No, these are 0605, but it also had some 04. These are 04. Look how small these are. I want to show you. There you have it. Open this in a new tab and just make a zoom. So this is a 0603 and this is a 0402. Look how small this is. It could be very difficult to solder with using your soldering iron. So that's why usually I don't use 0402. I just go with 0805 for the 10 microfarad, and if it's something smaller, I will go with 0603. So just take this one, we place it, and rotate it with R, and this will be between ground and 5 volts. So what I will do, just make this a little bit upwards, so it will be organized. Where's my schematic, my PCB, my capacitor? We place it here, and what I like is to place the ground. Instead of just making a connection to ground, I like to use more symbols like this. It makes it look a little bit more organized. So now we have a 10 microfarad capacitor between 5 volts and ground, and let's just add 100 nanofarad as well, and this will be a 0603. For example, this one. Obviously, if you want to also buy the part, you should check the price first. This is 0.2 cents, 0.2. Anyway, you should check the price as well. Placing that here. Copy this, paste it. And just like that, we have our voltage regulation. And it's also sometimes recommended to place a capacitor at the input as well. And where I should place that, just place it here and just copy and paste the input voltage, which is 12 volts. And this will be also of 10 microfarads because the battery could have some peaks, so you don't want that, and that's why you use a decoupling capacitor. And that will be our voltage regulated part. Just take the box, we close it in a box, and I also add a text, and this will be regulator. Voltage regulator, and place it here. Make this a little bit bigger. And we have our first part of the schematic. We know that we have a battery input, and then we have 5 volts output. Now, in the picture here, I told you that the battery input will be connected to 2 pads. I haven't placed that yet. So what I'll do, I go to the commonly used library, I go to pads, and I want the female pad, which will be this one here, but to be of only 1 pad. I select that, place it here. I don't like the name, so if you don't want to show this name, I will go here and we'll say display name. We change it to no. Copy paste this because we need 2 pads, and I'll connect one to ground and the other one to 12 volts. So then when we pass this to PCB, this will be 2 pads, which are this one, and we'll change the size of these pads, and that will be our main input for our PCB. So actually, just select this one. I like it to, yes, I'm a little bit obsessed with keeping it organized. Actually, I would change this to power input, because this is the entire power input part. We have the input pads, the voltage regulator, and so on. So now we have the first part of the circuit. The next part will be to add the microcontroller. As I've told you, this is using the ATtiny, so just search for the ATtiny 85. As you can see, designing PCBs is very time consuming. You can just stay 3 or 4 hours just designing a PCB. I think it's this one. No. ATtiny 85 altogether. Yes, this one. This is the microcontroller. I will just place it here. We know that this has to be supplied to ground. We copy paste it. I know that it has to be supplied to 5 volts. Copy paste it. We make the connections. Ground will be here. 5 volts will be up here. What other connections do we have? I will just check my schematic. We don't have any other connection, but what I'll do instead of drawing lines, what I told you is to use the net port. So I just copy paste it here, and this will be named PB0 because that's the name of the pin. Copy paste it a few times. Copy paste it, copy paste it. This will be PB1, PB2, 3, 4, and 5. So just like that, I'll make the connection to my microcontroller, and anytime that I copy this net port, I'll make another connection to any other part of the circuit. And I'll also add a small resistor. You can just use the resistor here. For example, just take a resistor of 0603. I'll place it here, and then I'll use an LED, 0603 LED. Because I want to add an LED to one of the pins. This one here is just fine. We add an LED, we add a ground, and this will be connected to PB4. So just copy PB4. And the reason that I'm adding an LED, because when you want to program a microcontroller that will do something, in this case, this will be a microcontroller for sending radio signal, you have to make sure that you are able to program the microcontroller. So before you just program it to send radio signals, which might not work, it's better to just program it to blink an LED. So this will be the LED right here, will be connected to PB4. So when I get my PCBs, I solder the component, I test if it works, if it blinks the LED, and that means that I am able to program that chip, and then I pass to the main code. So that's why I always add a resistor in series with an LED. The resistor should be of maybe 280R to limit the current from 5 volts. Also, the same I do with the caliper. So when I design a PC, I always have my caliper and also my calculator. And calculator is for something like this. For example, 5 volts divided by 280 ohms. It will be 20 milliamps of current. Maybe it's too much, so I will just change it to 200 Rs. So 5 volts divided by 200, it will be 25 milliamps, which is more than enough to bright 0603 LED. So this will be our microcontroller. We can just close it in another box. We can copy this text and place ATtiny 85, and that's it. And now we can just move it here so it will be well organized. And usually I also like to make these boxes the same size. It's not important, but my problems. And just like that, we have the microcontroller as well. Let me just check a little bit the messages once again, just to make sure that we don't have any other question, and I'll get back to you. Back to the schematic. Okay, so where we were. Okay, you can increase your audio a little bit. I'm not sure if why on the mobile phone the audio is very low. For example, I started testing with shorts videos, and when I edit that video, I place the audio at maximum volume. On my desktop, I can hear it at maximum volume, but when I run the same video on a smartphone, the audio is very low. So it's not my problem, it's something from YouTube. I'm not sure why the volume is so low. But I can listen to myself. You can listen? I can listen to myself, so the audio is very, very high. So it's not something from me, it's something from YouTube. So if you can hear me well, it's not my fault. Sorry for that. Okay, next question. Please continue the series about the smart solar charge controller. Yeah, that was a bummer because the solar panel controller was meant to be an MPPT, but finally it ended up like a PID controller for voltage. Basically, an MPPT should measure the input current, the output current, and always try to maximize the power that goes from the panel to the battery. And that project kind of did that, but not perfectly, and it ended up being something like a PID controller. And I want to make another one that is already made by a user on YouTube, but I want to improve it and use it with ESP32 because it has a lot more speed and using two different current sensors. But my list of projects is huge, so right now I'm not sure when I'll be making that project. Just stay tuned for that. I have that on my to-do list. I'm not sure when I will be able to do it. Okay, how to design an RF PCB like Bluetooth circuits. Okay, we should also talk about that. Let's just open one that uses just open a drone. For example, the V4, no, the V5. I think it's this one. So when you design something that uses radio frequency, I've tested a lot of parts, but you see, you don't want to interfere. This is the radio module. So imagine that instead of the NRF24, you just use a Bluetooth module, which I think is also 2.4 gigahertz. I'm not sure. But anyway, you are using a high frequency signal, like for example, a radio device like this one. So I've made a full video about how to take care of the noise, where to place the component when you're using radio. First of all, if you place it on top of your board, make sure that the power tracks, for example, this is a power track, this is going to a motor and it is using a PWM signal. So basically that will turn on and off at a very high speed, and that will create a lot of spikes, of current spikes. So a lot of magnetic interference and a lot of noise. So if you place your antenna above one of these tracks, you'll have a lot of noise and you won't get any signal. At the same time, you also have to be sure that you add a lot of capacitors at the input, so the supply of this device is very stable. Another problem that I found is the difference between the noise of the radio antenna and the noise between the connection and the microcontroller, the SPI connection. So I had a lot of noise on these tracks that are using a digital communication and not noise on the antenna. So I was receiving the signal okay, but the signal was getting out from the module and had a lot of noise. For example, these tracks are power tracks and are overlapping with the SPI tracks, which are this one here, and what they were creating a lot of noise. And another one thing that you should know is that placing the module on the outside of your PCB, I'm not sure if I have a PCB here, but usually when I have a Bluetooth device for music, for radio connection and so on, I place it on the outside of the PCB because the PCB will have a lot of tracks that create a lot of noise. Also, I was testing with adding a copper plane. For example, this is a copper plane here. Just place it on the... This will be a copper plane. And as you can see, it can create a lot of... Why didn't it create nothing? Just make it on the bottom side, round. I'm not sure why it's not filling it with copper. But anyway, if you fill the PCB with copper, usually you should reduce the noise. But I had a lot of tests, and adding copper would just create more noise because it will act as an antenna for other signals, and it will block the signals for the radio. So if you go to 3D view, as you can see, there is no copper between the tracks. You can just fill it, and usually it should decrease the noise, but not all the times. In my case, I had a lot more problems with copper plane than without copper plane. I won't save it, and we go to the next question. Please make a 12 volts 30 amps hour battery on Ultimate Designer. Okay, I had a question, but I'm not sure if you just see it or just deny my question. I haven't seen it. I'm sorry, I just jumped on it. What is your question? I need answer for low side shunt, bro. Using a shunt at high side of the bridge is not a better idea for short circuit protection. Why? The shunt is not The shunt is made to measure the current value. It's not for protection. If you want protection, just add a fuse. And you can add a fuse at the input, the positive input of your circuit. In this case, this is using AC input, and the shunt was placed between the grounds because measuring the input, if you have a loop of current, measuring the current on this side or on this side is the same because the input current is the same as the output current. So the shunt is used to measure current, not as a safety feature. So if you want a safety feature, just add a fuse, and yes, it is a lot better to place it on the top side of the circuit. Did you read The Art of the Electronics? No? Is that a book? By the way, I always get questions about what book you should read about PCB design, about electronics in general. I think I've read only 2 or 3 books in my whole life about electronics, and I never finished those books. I just read some chapters because nowadays all the information is online. So if I want to find this small information, instead of searching it in a book, I just Google it. And now with ChatGPT, you can find your answer in just a couple of seconds, and you don't have to read an entire book. If you want to read a book just to get more knowledge, I'm not sure which book to recommend you because I'm not a book reader. I read data sheets, I read other posts on the websites, and so on. So I can't recommend you any book. Okay, the quality of the stream is very good. I'm happy to hear that. Instead of having multiple flags next to each other, connect them together. That is just my decision. I mean, for me, this looks a lot better than connecting them together. And that's how I've did it since I've started making designs. And I think this is influenced because my professor was doing this as well. And I just copy that. I mean, I could just delete these grounds. It will be the same, just merge them together. And this will be the same connection. So I'm not sure why I do that. And I also want to be at the same height. I think these are just stuff that I do and is not very important. I'm on my laptop and your voice is still too low. But I'm not sure why is that that is happening. I mean, can you hear me? And these are just headphones. The audio, actually, I should lower my voice because it's the voice is very high. So I'm not sure why you are listening to me that low. Okay, anyway, as you can see, we just continue with our schematic. This will be the final schematic that we should make. And instead of making the entire schematic, we will be spending here like 2 hours. What I will do is to open the original schematic, which is 400 RX. Yes, it was the RX. So this is the original schematic. And for example, we go back to our schematic. I want to add this part here. And this is a voltage regulator. This is the RS schematic. This is a voltage regulator that you can find on AliExpress. I think it's 220 volts to 12 volts module, something like that. Yes, it's one of these modules. Not sure which one. Not this one. Where is that module? It was blue colored, right? I think it's one of these ones. Anyway, this one. Yeah, I think it's something like this with 2 pins here and 2 pins at the output. No, this is the input and the output. Well, if you try to search this on the library, what you will search: 220 volts, 12 volts converter. As you can see, it didn't find any result, but if you go to user contributed, you might find one that suits your needs. But in my case, as you can see, this is not exactly what I want. So what I will do is just copy this, edit it to fit my requirements. So just clone it, and you give it a name. 220 volts AC, 12 volts DC module, I will call it. And this will get saved into my workspace. So if I go to my workspace and search for it, this is the module that I've just cloned. No, this is the module that I'm using for my 120 volts. And this is the module that I've just cloned. So I will be editing this the schematic symbol and the PCB pad, and then I'll import that to my schematic. This is just in case that you don't find the exact shape of the component that you want to use. So first, let me just click the PCB schematic. And I think this is quite good. The only change I will do is to place this at the same height. That will be a lot more organized. And maybe place the number closer to the pad. So this will be our symbol. We just Control S for save. We can exit this. Sorry for that. This is our schematic. And now we click the PCB pad. Click this here. And as you can see, this is not the exact shape that I want here. I want 2 pads here and 2 here. So you should get your module, which I don't have right now. Using the calipers, you measure the distance between the pads, or you can find maybe a user manual of this symbol of this module with all the sizes. But I know this is 29.8 by 22, 21.2. So we go to our designer and we measure that. We make this to be 28 by 22 more or less. And I know that the input will be on this side like this, and the output will be on this side. Obviously I'm doing this very fast because it doesn't have to be perfect, but in your case you should measure the distance between the pads, and then using the measuring tool you just come here, you measure it, and it's 3.55. I think this is 2.54 it should be. So just move it around, and also you can place this, you can see the origin is centered on X 2.54. So this will be 2.54 plus the distance between the pads. So 2.54 times 2, 5.08. And now it is at exactly the distance that we want. And for Y is minus 20. So we copy that here, and now this should be the distance between the pads, 2.54. You can also move these symbols here. The voltage output, I can rotate it. This will be a plus. Where is the plus output? No, the plus is this one. So this will be the positive, and this will be the negative, and do the same for this one at the same height. Copy and paste it, AC. Also measure the distance between these pads. Use your caliper once again if you want to precisely know the distance. And this should be the symbol for our component. You just save it, and when you save it, you should give it a new name. Converter PCB symbol. You save it, and now we can close this symbol. And if you go to library once again, you will see that this component still has the same pad here. So what you will have to do is to place it on your schematic. And here, what it says footprint, just click this part here. It will open the footprint that it has right now, which is the wrong one. You don't want this. And then you go to your workspace and search for the component that you have just edited, which was this one. Let me just make it a little bit bigger. It was this one, PCB symbol. You select it, and it will automatically connect the symbol schematic with the PCB layout. And just like that, you could create any component that you want. You click update footprint, and now this component, as you can see, if I refresh, it has the component that I've created. You can place it anywhere that you want, and just like that. No, this is not the same one. This is the one. This is the one. It didn't update it. Why not? Library, place. Not sure why not. Footprint, search. This is the PCB symbol. Update footprint. And now it should work. If I open this footprint, now it's okay. Now it has a footprint that I wanted. So just like that, you can create any component that you want. So let's just say that you find a transistor that it has a very special pad, and you don't find that here. So you just click this schematic and you can add any other pad that you want. For example, you just add a pad here. You can make it, for example, if it is an SMD component, you just make it, instead of multi-layer, top layer. Instead of round, you can make it polygon, and maybe give it a size of, no, not polygon, rectangle, a size of 2 by 1. So for example, this could be a pad for transistor. Just copy and paste it, and just like that, copy and paste it. This will be 3 by 2, something like that. And all you have to do is to, for example, go to AMS 117 datasheet, which is this one here, and this could be applied to any other component. Anytime that you find a component that you don't have the pad for, you can just make it your own. This will be the pad, and usually on any data sheet you can see the sizes and the distances between the pads. As you can see here, you have all the sizes of your pads. You have the size of the component, the distance between the pads, the distance between these pads and the top of the top pad. So all you have to do is to just go here, change the size of your pad, and then using this one, you can measure the distance between each one and place them exactly in the position that you want. Then you can just change to top layer, silk layer, maybe make a square like this. And that will be pretty much a component for your schematic. But have in mind that each pad has a number. And if we open our schematic from before, where it was this one, as you can see, this pin is called 1, 2, 3, and 4. So when you make your schematic, make sure that your pads have the same name. For example, this is named 5, 5, 5, and 5. So if you want this to be 1, 2, 3, and 4, you have to change this number to 1, this to 2, this to a 3, and this to a 4. Otherwise, when you make that thing that we did before, but to select the footprint of your schematic, as you can see, this already related that the pin 1 is connected to pin 1, the pin 2 to pin 2, the pin 3 to pin 3, and pin 4 to pin 4. If you add a pad like this one, that it has number 5, 6, or any other number that the symbol is having, it won't relate that automatically. So you have to make sure that the number of the pad on the pin of your schematic is the same as the number of the pad of your PCB schematic. So just like that, you could make your own components. Okay, so instead of making the connections once again and lose a lot of time, just we pass directly to the made schematic. And now if you have any question before we pass to PCB, and now is the time to ask a question. So let me just go here on the video. So if you have any question about this schematic or about connections, about how to organize your schematic, now is the time to make it. Okay. Your audio is fine. Okay, so there are people that are hearing my audio okay, and someone that is not hearing the audio okay. Anyway, please make a video on this topic. What topic? What topic are you talking about? If saving space is needed, stick to 0603 resistors. If there are multiple resistors nearby, use a network resistor. Yes, you can also find a network resistor, which basically are a few resistors merged together in the same component. You can also use that, but I think those resistors are always the same value. I'm not sure, but I think that are always the same value. You are the best product development evangelist in the world. What? Love to see your informative videos and contests. Thank you. I'm not sure what that has to do with electronics. Please lead me in the right direction. These tips are OP. Which are software are you using? This is EasyEDA. It is a free software, Actually, it's not even a software. I mean, it's a software, but it's online. You just go to EasyEDA.com and you can work directly there. To build efferent stepping in inverter 448 DC to 125 VAC 30 amps and 5 amp steps efficiency, please. So I don't understand this type of questions because they don't have a comma, and I'm not sure what you want from this. How do you select your physical connector size for 5 volts projects? Well, depends on the project. I mean, for example, for my multimeter, the multimeter, it was obvious that I wanted to make the input to be as big as possible to add this kind of connector, because this was just an SMD pad connected to a metal rod. So once I am in designing the PCB, I can change the pad size according to what I want. Once again, these are 0402 capacitors and resistors. So I'm not sure what you want to say with that. How do you select the size for your 5 volt supply? I'm not sure if you are referring to how much current that they will withstand. Anyway, R3 should be on the other side of R4, really. Why is that? How do you select the physical connector size for your 5 volts project? In software, I mean. The physical size of the connectors. I have a cat here. I think he's hungry. I'm not sure what you want to say about that. And this connector is a normal connector as any pin as for the connectors for the Arduino. I mean, go to pictures. This is a typical connector, a typical pin connector. So anytime that you add on your software these female or male connectors, it will be that size. This is just one pin, and you can select 1, 2, 3, 4, up to 20 pins. I'm not sure what you want to say with that. What version of the Arduino IDE you recommend? Not sure. Let's just see what version I'm using right now. I'm not sure what version I'm using. Let me just open Arduino. It's not the latest version, and I don't want to. Is the 1.8.15. I don't want to upgrade my version because sometimes the libraries that I'm using will fail. So sometimes I just download the downloadable zip version of the software and just use that. You've created a voltage divider with R3 and R4, so the base resistor is also sinking current into R3 when high. R3 and R4, where are you seeing that? R3 and R4. Okay, this is a voltage divider. I wanted a voltage divider. I wanted a voltage divider. So what? So this is a pull down, and this resistor is connected at the base just to limit the current, and it will be a voltage divider. So if this is 5 volts, maybe 2.5 volts will be at the base, and that's more than enough because this is the BJT transistor, and with the small current that will pass here, it will open. I'm not sure what's wrong. Actually, this is not my schematic. This is the same schematic from an SSR module, and I'm not sure if I can find it. This one. So if you take this schematic, the resistor here, the diode, and the LED, this is the same schematic as I have here on my schematic. So I'm not really sure what is the problem. I mean, I do have a voltage divider, but that's not a problem. And not sure what you suggest. How you would do it. without this resistor here, just a plain connection directly to the base of the transistor. I mean, you need a transistor as a pull down, so when this is not connected, this will be turned off. And you also need a transistor to limit the current, because otherwise this is a BJT and the base of the BJT is opened by the currents, and you don't want to place a huge amount of current here when you want to turn it on. Anyway, what is your opinion about Giga Arduino? I haven't used it yet. I've ordered one, but I haven't used it yet. And I've also ordered that new Arduino Nano, which was called the Arduino Nano Zero or something like that, which is very new. I also have a problem choosing the package of components, for example resistors, whether choose 0805. I'll be just back. I have to open the door. Okay, so I'm back. I already received a lot of products. I just received a new box, and I've just received another box, another bag, like 1 hour ago, with some new components. And by the way, I also want to make like maybe a live mailbag video, or just a mailbag video without being live, where it will be just me opening components. For example, I just received this thing here, which will be for a very interesting project. Stay tuned for that. And what do I receive? These two multimeters. And I'm not sure what I have inside of this bag. This should be interesting. It's not, doesn't weigh too much. Okay, so now that we have the schematic, let's just pass to PCB and learn how to make the tracks. So what you'll have to do is to save your schematic. We go to design, convert schematic to PCB. It seems that there is a problem. Let me just check the nets here. Oh, the problem is that I have two schematics, this one and this one. So what I will do is to just delete one. So the sheet one, I will delete it. And now I'll go design, convert schematic to PCB. And now this will take all the components and place them on my PCB design. What I like to do is to move them here on the side. And the first thing I do is to select the size of my grid. So just click here, canvas properties, make sure that you are in millimeters or maybe in mils, but I'm not sure how much a mil is. So I'm used to using millimeters, so make sure that you are in millimeters. I want to have a visible grid, and usually I leave this as it is because 2.54 is usually the difference, the distance between normal pins. So for example, these Arduino pins are 2.54 distance one to each other. But if you want, I also can change it to 1 millimeter. And then the snap size. The snap size is when you move a component, as you can see, it can snap into place. Let me just change it to a different value, just make it 2 millimeters. So each time that you move it, as you can see, it jumps 2 millimeters. So that's very useful, but you don't want to leave it to 2 millimeters because if you want to place it exactly here, as you can see, you won't be able because it will jump 2 millimeters each time. So usually what I do is to make the grid size to be 1 millimeter and the snap size 0.1. And like that we have exactly a grid of millimeters, and then each time that I move it, it will move 0.1 millimeters, and that's very useful. But obviously you can also leave it to 2.54 if you want the distance between the pads to be 2.54. The next step that I will do is to place the PCB exactly in the middle. So for that you go to Tools, Set Board Outline, and let's just make it, this size will be different when we finish the PCB, but let's just make it 60 by 30. So the start point X will be minus 30 and the Y will be 15. And as you can see, it is exactly in the middle of the grid, and that is just my way of doing the PCB design. Let me just open the YouTube for a moment. Or just using, wow, oh, I got a 3 volts dial gauge and it works awesome with Arduino and ESP. Put an X on unused pins. Yes, that should also be useful. I'm building e-bikes and I have a 48 volts DC. I need to build a stepping inverter to 125 VAC to 30 amps. I'm trying to ask you what type of circuit you want and how to find the schematic for a stepping inverter trigger circuit. Well, actually this PCB that we'll go over in a few moments, this is an inverter. So what you want to do first is get the voltage of your battery, create high voltage. In this case you want 120 volts AC, so maybe you have to create 220 volts. You store it into some capacitors, and then using IGBTs you create the AC signal, which could be a square signal, or in this case is an SPWM that will create a sinusoidal signal. So maybe this will help you. So this weekend I'll post this project and maybe this will help you, because it is a high voltage inverter. From battery it goes to, in this case, 220 volts AC. How to decide the size of the tracks, because I don't know how to calculate it. That's very easy. You go to a website, let me just search it. PCB trace calculator. This will be. So basically you have to know how much current it will withstand. In this case, let's just say 2 amps. And the thickness, no, I want the opposite of this. I think is this one. This is also useful. As you can see, you can enter the width, the length of the thickness, and it will give you the resistance. I've used this website for this PCB here because I wanted to know, this will be a Tesla coil. Stay tuned for that. I wanted to know the resistance of the entire wire. So as you can see, this is very, very long. So I know that the wire is of 0.14 millimeters. I know the length of the wire and also the thickness of the copper, because for example, if you go to PCBWay.com and you go to quote now, as you can see, you can select the thickness of the copper. So the finished copper is just 1 ounce of copper. So if you go to that page here, you can select it to 1 ounce feet squared. The length trace, let's just place it in millimeters. I think it was something like 800 millimeters, and the trace width was 0.14 millimeters. And the temperature, I don't know, normal temperature of 38 degrees. You click calculate and you have a resistance of 2.92 ohms. That's pretty much this kind of calculator you have to use when you want to know how much current your PCB will withstand. Obviously, in this case, the track was a lot thicker because this has to withstand 500 watts. So use this kind of calculator to get how big your track has to be in order to withstand the amount of current that you want. Okay, I hope that this will solve your question. There's another page that instead of placing the size of the track, you can just place the current that you want to withstand, and it will give you how thick the track should be. So you have both type of websites. Okay, so let's just start. The first thing that I do once I have my PCB, I decide where to place the components. Obviously, I will have an input and then the controller output. Usually when you have a microcontroller, you will want to place the microcontroller as center as possible. So this will be something around here. And then you have the connectors on the outside. You don't want to place a connector in the middle of the PCB. That's not very clever. So usually the connectors will be on the perimeter of the PCB. So this is the input connector, yes. Let's just say that I will place it right here, and I will hide the prefix because I don't want to see it. The connector here. The radio also, as I told you before, you will try to place it on the outside of the PCB as well, because you don't want to interfere with the PCB, the rest of the power connection, especially when you work with high voltage. So remember, this module here has AC input of 220 volts, and that will create a lot of noise, so you want to keep your radio connection as far as possible. So I'll place it here, and then I'll make the PCB just a little bit bigger. Doesn't let me. Just a little bit bigger. Anyway, I'll do later. The first thing is to just select where to place the components. I'll move this one as well. This will be the SSR, which should be close to the high voltage input. Just place it here. We also have a button, which doesn't matter where we place it. Just make the PCB a little bit bigger because it's too small. Make it of 80 minus 40, 36, and this should be 18. Just like that. The PCB was too small. And also, if you want your PCB to be round, you can just go here into Tools, Set Board Outline, and instead of making the round or circular, just make the merge together, round and circular, and just place a radius of, I don't know, 4 millimeters. And as you can see now, it's also round on the edges because that looks a lot cooler. The radio will be here, this one will be here, this will be the output. I'll place this output connector, this will go to the load here. Now we place, this is the LED that I have told you before, should be closer to the component. Just rotate it, just like that. This will be the LED. This went with a resistor, which I think is this one here. Make sure that you place the name of the resistor so you could see it, because if you place it like this, when you solder the component, you won't see it. And this is very important because when you solder the components, you will see the schematic and then your PCB, and you want to see the seal clear to know which resistor each is which. So make sure that it is very visible. And if you, for example, have two resistors close together like this, make sure that you place the name in front of that resistor, because, for example, if you place it like this, if you just see something like this, you don't know if this R2 is for this resistor or for this resistor. So make sure that you may place it on this side or along the resistor, like this, in order to know which one is which. The voltage regulator, I will place this voltage regulator on the other side of the PCB. So all you have to do is to select it. You go here, and from top layer to change it to bottom layer, and it will change the color to blue. So that will be here. We know that we'll have 12 volts from here, so we can place it here, right? Like this. This will have, this is the diode for the control. This will have an output and input capacitor. This should also be on the bottom side, so change it to bottom layer. No. Entire capacitor, change to bottom layer. Rotate it. And then the other capacitor should also be on the bottom layer. I mean, it's not mandatory, but I want it to be on the bottom layer. Now we have our power supply. This will be the input. This will be the output of 12 volts connected to the voltage regulator, and this will give 5 volts for the rest of the electronics, which will be on this side, separated for all this part. On the bottom will be high voltage, and all this part on the top will be of low voltage, 5 volts, and you want to separate that. And this is another diode for the control. You can use these lines to know more or less where each one will go. This is the transistor connected to the diode, like this. I'm doing this very fast because it's not very important. As I told you, I just want to show you more or less how to place your connection. R4 will be here. R5 is connected to the button, so just place it here like this. And this is a capacitor for the radio module. Oh no, actually this is a capacitor for the power supply, so I'll just place it on the bottom side as well and get it closer here. Okay, just like that. And these are the paths for the SPI communication in order to program it. So what I will do is to hide the text because I don't care about the text, and just place it very close one to each other. By the way, if you have any question, just ask it and I'll try to make it, to solve it for you. Okay. The final PCB should be something like this. So I'll place these pads on the bottom side. As you can see, these are the pads for programming. So just take them, rotate them, and place them maybe here. And now we will have our PCB, more or less. I'm doing this very fast. Usually I would spend a lot more time, but since this is just a quick tutorial and show quick tips and tricks, I won't spend too much time. So now you have two options. First is to route it automatically. And by the way, for that, you can just download the EasyEDA pack. You go to EasyEDA and you download this pack here. And you run this Win64 and this will make it a lot faster. Because this will execute all the commands on your PC. So you can just go to root and just go to automatic, auto root. And when you click run, it will automatically make all the tracks with the same thickness, which is by default 0.25. And as you can see, in just a couple of moments, you finish the PCB. But this is very wrong. First of all, as you can see, we have a lot of ugly connections like this one, which you don't want. And second of all, the program doesn't know that these are power tracks. You don't want 220 volts to pass through a 0.25 millimeter copper track. You want this to be a lot thicker. So let me just Ctrl Z on this one. If you really want to use the automatic route, you could also select some rules for the designer. So before you run this, you go to design rule check. To route. Where was the rules? Design rules. As you can see, the rule for the first rule is that the minimum track will be 0.25. The clearance is this one. By the way, the clearance is given by your manufacturer. So for example, PCBWay, you go to capabilities, you go there, here down, and we should find the clearance for our PCB. So minimum spacing is 0.1. So you should know that the minimum space between the tracks is 0.1. In our case, is 0.15, so we are good to go. Usually I make this 0.25, 0.15, the via diameter is 0.6 and 0.3. All these rules you can find them here. The via hole, the track, the minimum track width, the minimum track clearance, and so on. So you can place this here. But then you can make a different rule. So you just add one and you call this power. For example, VWR. And this will be 2 millimeters thick. The clearance will be 4 millimeter. The via diameter will be 1 millimeter, and the drill will be 0.5. And if you want to apply this rule only to a few tracks, you should select those tracks. So for example, the AC signal should be set to power, apply, and this AC signal as well to power. And now if I apply a setting and go once again to root, auto root, it will make all the tracks 0.25, but the AC signal track will be of 4 millimeters. And you should do this for each track that you are making. and I think this time it will have problems because adding a 4mm track is very difficult. Let's just see it will be if it will be able to make it. It wasn't able to make it, so that's why I don't use the automatic router, because all it had to do is to just use a 4mm track like this one. Why it doesn't let me to... I think I've placed the clearance of 4mm. Let's just change it to 2. And this will be 2 as well. Now I could make it. That's why I didn't make it, because I had a 4mm clearance. This is AC plus. Why it didn't let me connect it here? This is stupid. Change it to 1. I mean, the distance between the tracks could be of 4mm, but the distance between the pads is not, because you can change the distance between these two pads. This is a component that already has the distance made, so that's why I couldn't make the connection, because when I get closer here, as you can see, when you click it, you have some sort of circle around it, and that will tell you the clearance that you have edited. And if this was set to 3mm, it will touch the other pad, and that's why we couldn't make the connection. So instead of making an auto route, what I will see, what we'll make, I will unroute them all, and we go one by one. So let me just teach you how you should make your manual route. You click the route pad, the route button. Just make, first we start with the power connection, and I really want the power connection to be of 4mm, and I will leave the angle of 45 degrees. You can change it to 90, but it is a lot better to make a 45 degrees, especially when you are working with high frequency signals. So the first part, I will connect all the power, so from this connector to the regulator and to the output. So we start with the track, we select the top layer, and just like that, let me just delete the other rule because I won't use it. So just like that, we go like this. The first connection is made, and the other one something like this. And as you can see, I have my first connection of 4mm. We don't have enough space here, so maybe I'll change this to the bottom layer. So now we have 4mm, and we also have the PCB, which is made of plastic fiber in between. So we have a lot of insulation. I'll just move this to the side like this and place them a little bit here like that. And the other power connection of 4mm are between the SSR. I will go on the bottom layer. To change between layers, you can use just these two ones. We go like this. One is connected, and on the top layer we go like this. Actually, I think I'll place this on the top layer. And the other one on the bottom layer. And here, when I change to the other layer, it will automatically add a via, which is a little bit smaller. So I'll change it to 1.2, and the hole will be of 0.5, for example. So just like that, we've made our power connection. And now we can go to the low power connection, which will be 0.3 in my case. 0.3mm is more than enough. And we start just routing manually. And as you can see, I've selected the position of the component, so this will be very easy to make. So just select the bottom layer here, connect to the PCB, to the capacitor, voltage regulator. This is the ground connection, ground here. Okay, for this we should make a top connection like this. Then we pass to the bottom side. Once again, I'm doing this very fast. This once again will go like this. On the top side, we add a via like this. These vias now are too big. 0.9, 0.6, 0.4 better. Yes. 0.9 and 0.4. Usually EasyEDA, if you change the size of one via, it will keep making the other vias the same size. So since I've changed this to 1.2, it will make this one to 1.2 as well, but we don't want that because this is just a signal connection. We keep routing like this. Anyway, you see how this works. So instead of just finishing this and lose a lot of time because it's already almost 3 o'clock here in Spain, I will just skip and jump directly to the PCB that I've made for this project, which is this one here. And on this PCB, I'll explain you some tips. Then we go to the high power one, which is this one. I'll explain you some more tips and so on. Let's just open the other design. To hide one of the layers, just click here on this eye. We'll hide the silk layer. And this is the design for my PCB. As you can see, I've been using 3mm tracks for the power tracks and also 4mm in between. If you want these tracks to withstand more power, let me just open the 3D view. As you can see, we go on the back. This track is covered with the silk layer. So the power will be withstood by the copper. So if you want to add more copper, one way to do is to expose this track, and for that just select the track that you want to expose, and you can see here that we have this button here, exposed copper. When you click it, it will automatically create a solder mask for that. So if you save this and open the 3D viewer once again, you will see that now this track is exposed. So you can just get your solder and add a lot of solder on top of that. Actually, I have a video for you. Let me just search it. I have a video with my new project because this PCB here, if we open it in 3D, actually you can see it here. This is the PCB. As you can see, it has a lot of components, and this will use 500 watts. So we need a lot of power to go through these tracks. So instead of just ordering a PCB that is very, very expensive with a lot of copper, just expose the tracks like this one and just fill them with copper, with solder, I meant. So I have a video for you where I'm filling the lines with solder. Let me just search it for you. Let's see if I can find it. Okay, so this is the video. And as you can see, just take that track and add a lot of solder, and like that, this track will be a lot thicker and it will stand a lot more current. And this is the cheapest way to do this. Just expose the copper and fill it with solder, and the more solder you add, a lot more current it will withstand. So anytime that you want to do that, just select the track that you want to make and click the expose copper. So let's just expose all these power tracks. We save it, and now if I go to 3D view, you will see that on the bottom side the power tracks are exposed. Obviously in this case this is very dangerous because you have exposed tracks, but having exposed tracks is not more dangerous than having exposed pads with 220 volts, because if you were to touch this PCB, you could touch it here the same as you would touch it here. So be careful if you do this project and you are working with high voltages. Be very careful and make sure that you never touch the PCB while it's connected to high power. Actually, I had a lot of bad comments on this project because a lot of people told me that this was very dangerous. But you should never touch this PCB. Why would you touch such a PCB when it's connected to power? Usually what you will do to install this PCB is to go to your electric box, just pull down all the fuses, cut the power for your entire home, install this, connect the wires, install it in your wall or in some sort of insulated box, connect it to your light, and then turn back the power, and never touch the PCB. Actually, if you go and search for Alexa light switch, something like that, module, for example, this one. This is pretty much the same that I have, but instead of radio it also has Bluetooth. And if you take a look at this is also high voltage. This is a relay for high voltage, and it has a lot of exposed pads. But this is a commercial product. You should never touch those pads. So just by making something dangerous doesn't mean that it has to be dangerous if you work with care with that component, if you use it properly. Anyway, that's what I wanted to show you, how to expose the tracks. What other things I wanted to show? For example, when you work with high frequency signals like the drone, this drone here, any upcoming drone project? Not sure, I don't think so, because I had like 10 videos about drones. I made the brush drones, the brushless drones, the Arduino drone, a drone with a commercial bot flight controller, the mini drone. So I already have a lot of drones and a lot of radio controllers. So I'm not sure if I will make a new one. Only if I will have a new, very different idea. So if you have an idea, just tell me about it and maybe I will put it on my to-do list. By the way, this is just coffee. Okay, so for example, for this project, this is using high frequency signals. So you want these tracks to be of 45 degrees because high frequency signals are getting a little bit strange when you are using a 90 degrees angle. So for example, if you make an angle like this, 0.2, if you make an angle like this, high frequency won't like this angle too much. It's like a car going at high frequency and won't be able to make the curve. So usually it is a lot better to use 45 degrees angles. Also, and when you want to have very synchronous signals, for example, if you have a track like this is connected from here to here. Sorry, let me just change it back to 45. So imagine that you have a track like this, and you have another signal that's exiting, I don't know, from here, and it goes like this, like this, like this, to this point. So if these signals, you want these signals to get here at the exact same time, and also to have the same resistance, you need to make these tracks the same length as this one. So usually what you will see on some PCBs is some sort of zigzag. So instead of just going straight here, you will go like this and make some sort of zigzag. Let me just make it again a lot more beautiful. Actually, with 45 degrees it will be better. So you can make some sort of zigzag like this. This is very ugly, sorry. Anyway, I'll do this very fast because I don't want to waste any time. So then the length of this one and the resistance of this track will be the same as this one. So like that you will you will make the synchronization a lot faster, and also the impedance of those tracks will be the same. Let me just search for zigzag PCB track. Something like that. For example, this one, actually this is for buttons, it's not the same. These are pads for buttons. So anytime that you will see a PCB that it has some sort of zigzag, that's for synchronization and also have the same impedance for the track. So the resistance of the track will be the same. Something like this. Anyway, let's go back to our design. We delete this. So what I wanted to tell you is that it is a lot better to use 45 degrees instead of 90 degrees. What more can I show you? how to add external pads. For example, this pad here is not connected to is connected to nothing, and this doesn't appear on the PC on the schematic. But these are just some holes of 3 millimeters instead, that in case that you want to screw this on some sort of case. So all you have to do is to just click the pad button and place it here. But as you can see, it will give it a name, it will give it a number, and the name usually is ground, but in this case it's nothing. So if this were ground, GND, as you can see, it will tell you that this is not connected. So all you have to do is to change it nothing once again and change the size. In my case, it will be of 3.2 and the hole will be of 3 millimeters. So as you can see, this will be the pad for 3 millimeter screw. And how to add images. For example, on the bottom layer, let me just hide this, I have this picture of my icon. So what you want to do is to have the picture in a PNG format or black and white. So you go to that layer, in this case the bottom layer, and you click the picture here, and it will tell you to open an image. Let me just go to my my pictures, and here I have this icon. Insert it to picture team where it is. Okay, as you can see, it's huge, and just change the size 22, just making 11 by 22, and just like that you add a picture to your silk layer, and you can rotate it if you want and place it wherever you want. Let's just see if you have any other question. I have a question. During routing, do you follow schematic, like from power source to capacitor to tiny, or just based on the net? Well, when you want to route your PCB, the first step, as I've showed you before, is to select where to place each component. So for example, I knew that the input will be here, the voltage converter will be here, the SSR will be here, and the output here. And that's basic logic, because you don't want to have this component with which is the SSR on the other side of the input. That doesn't make any sense, because you have to go from the input to the SSR, and from the SSR back to the output. So you have to just think more or less where to place each component. So basically, when you route your tracks, you will follow the schematic, but at the same time you will follow logic, because you want to know how your track will be, how short it will be, the position where you want it to make, to place it. For example, this track I could also pass it through here on the up part of the PCB, but you don't want that, because I want to avoid connection between the high voltage part, which are these tracks, and the low voltage connection of 5 volts. Okay. What about having insulated wires instead? Not as pretty, but safer. What are you talking about, insulated wires? Are you talking about the exposed tracks? Make the connections with wires, or what are you talking about? Someone has never worked on a power supply if they are complaining about this design. Yeah, just go to that video and check the comment section. It was something like, how can you share such a design? This is very dangerous, you could kill people. I mean, yes, it's work with 220 volts. That's why I've dedicated a full minute of talking about please use proper tools, never connect power while you're touching the board, be very careful. If you're not sure what you're doing, just don't make it. But this is a high voltage board, so it will be dangerous, so treat it with care. Just because it's dangerous, it doesn't have to kill you if you know what you're doing. The exposed copper was covered by silk mask. Your icon looks like a superhero. You mean on this PCB? No, because where you have exposed track, the silk layer won't appear. So for example, here, this won't appear. I'm not sure if I can show an example on this PCB. Yes, maybe on these MOSFETs here. Let me just place the OBS so I can see the picture. These MOSFETs here. Oh, this won't focus. Anyway, the steer clear of the MOSFETs won't appear on the tracks because anytime that you have exposed copper like this one, the steer clear won't appear. On this 3D animator it will appear, but on the real PCB it won't. Don't worry about that. Let's just see other questions. Is there a specific reason you prefer EasyEDA and not KitKat? No. I've used KitKat as well. I've used Design Spark, Altium. I just use this because it's very easy to use online. And also, as I told you at the beginning of the video, I like the user contributed library because here you can find a lot of modules that usually don't appear in basic PCB design software. For example, you just write I2C OLED, which is a very common display that I use, and you already have the PCB designed for this OLED display. And usually in Design Spark, KitKat or Altium you won't find that. You will have to make it yourself. So that's another bonus that you have with EasyEDA, but I don't use EasyEDA all the time. Sometimes I make my PCBs in Altium. For example, I made this PCB coil. By the way, I also want to talk about this one in Altium as well, because that's a lot easier to make this round shape. Actually, this is taking so much memory from Google Chrome that sometimes it crashed because it has so many tracks that is very difficult to work with. But in Altium it is a lot easier to make the circles or the spirals. By the way, if you want to make this, you just go to your schematic, to your PCB design, and instead of using a normal track, you click the circle one, which is this one here, arc center, or this one here, and you place it one here, and then then you go where you want the circle to end, you place it another one here, then you start here and end here. That was made in spiral. So just like that, I'll be making the entire PCB. Obviously this took me once again 2 hours because it has like 200 spirals. If you take a closer look, let me just take this out. As you can see, it has like 200 spirals. So this was a lot of work, but basically that's how we can make a spiral using the arc tool. If you have any other question, will this video be available to watch later? Yes, this will be saved on my YouTube channel. The sharp angle track is okay as long as the signal is below 1 GHz. Thank you for that tip. I didn't know that it was that high. I thought that with megahertz you would already have problems, but I trust you. So if you work with low signals like maybe 1 megahertz, you don't have to make 45 degrees angle. But for example, for 2.4 gigahertz, like maybe a radio connection, you should work with 45 angle signals, tracks. The HV doesn't seem as insulated with such long HV tracks. Yes, that's also true. I mean, it's better to have insulation over the entire board, but not all the pads, compared with not insulated tracks all the way. It is a lot more dangerous. I understand that. That's why on the final PCB, which is this one, as you can see, I haven't made exposed tracks. Where is the receiver PCB? This one. It doesn't have exposed tracks because it won't control that much current. This works with 220 volts, and the SSR here can only take up to 2 amps. So with these tracks is more than enough. Why don't you use an X file instead of old HTML? For EasyEDA, I don't think they have an X file. I mean, it's not an X software. I'm not sure if they have one. That's why I'm working directly on the online version. Bro, what is MISO and MOSI? It's master input, slave output, master output, slave input. Those are the pins for an SPI communication. So if you search SPI communication, as you can see, we have, this is the master, which usually is an Arduino or a microcontroller of any kind, and you can connect different slaves. They are called slaves. That's an awful word for a chip, to be a slave. Anyway, so if you want to talk to this one, you enable a chip select of this one, and using the MOSI and MISO pins, you can communicate back and forth, and like that you can connect multiple slaves to the same master. That's what MISO and MOSI is. How can I customize the board outline? Not like, oh, that's a very cool question. Actually, the transmitter of this PCB and transmitter is this one here. And as you can see, it has an unusual shape. So what you will do, you will start, let's just start with a square one. Let's just open File, New PCB, and make it 100 by 100. So if you want to make an original shape for your PCB, if you go close to the outline, if you make just one click, it will turn white. And then if you make a double click, like this, when it's white, you make a double click, you will add another point, and you can move this point all around. So for example, you can place it here, and then you can make here another point and place it here, and you can play with the size of the grid. For example, let's just change it back to 1 millimeter, 0.1, 0.1. So in this way, you will know that each square is 1 millimeter. So place it here, and this one, place it here. So as you can see, we are starting to have an original shape. And for example, you can move this down here, this as well. Basically, you have to add a lot of points. And then place it here and here. So maybe this one on the inside. What happened? So as you can see, we are starting to have a more original shape. If you want to add another point, just go close, double click it, add another point, just move it around, double click it, add another point, just move it around, and just like that you can change the shape to anything that you want. For example, this one here, all I have to do is to just add this point here, add this point here, and just like that you can change the outline to anything that you want. And if you want to add, for example, like the FOC project, look at this design. Let me just open it. As you can see, I have the outline and then another separated PCB, and also on this other design I have the same exact PCB but also added some vias. So when you ask this to be manufactured, you will receive this PCB, and all you have to do is just snap this PCB and break it, because this part it's supposed to go over here between these pins on top of the PCB. So instead of just making two PCBs and pay double the money to the PCB manufacturer, I've made two PCBs on the same design. So I send this to PCBWay just as it were one PCB, and then just use these vias here to break the small PCB and place it here. That's another idea you could make just by setting the outline of the PCB and adding these vias here, so you could break it easily. Now I should maybe talk about this PCB if you have any other question about the tracks. I've already shown you how to expose the copper, so it will withstand a lot more current. And by the way, I've told you that the connectors should be on the outside. You should never place connectors in the middle of the PCB, because that's very ugly and very uncomfortable to connect. So the driver always in the middle, or the microcontroller, the connectors on the outside. This is a connector for the output, this is a connector for the input. The capacitors, the decoupling capacitors, should be as close as possible to the driver, because anytime that it needs power or it has a voltage spike, you need that capacitor very close to the driver, so it will keep the voltage supply very stable. What other things I should tell you? The track should be 45 degrees. The exposed copper is very dangerous because you could touch it. What any other stuff can I tell you? We'll make a DIY SMPS video. Maybe And I think I've made a power supply before with an Arduino, but I'm now planning to make one with an SPS32, which has a lot more power, a lot more frequency, much speed. And that's the problem with my previous power supply, because I didn't have enough speed, so the voltage output feedback was not didn't have the enough speed to control the PWM output for the controlling the MOSFETs, and the loop was getting slower and slower. But with an SPS32, I think that I will have a lot more speed, so maybe we'll have a power supply with that as well. Oh, by the way, another thing that I wanted to show you. This is the 3D view of the PCB, but I didn't have the capacitor, I didn't have the transformer. This actually, I've made this in Blender. I didn't have this coil here. So for example, you go to GrabCAD, let me just sign in here. So this is GrabCAD, okay? What's this? It doesn't work. GrabCAD website doesn't work anymore. Why is that? Okay, this is GrabCAD. So you search for transformer or capacitor. I'm dyslexic. And OBG. So for example, you can download this capacitor here. 3D design. Download file. And you can see I've downloaded the 3D file for this capacitor. And then when you go here in your schematic, let's just say that this capacitor here doesn't have a 3D design. So you go here to the 3D design. No, on the schematic directly. This capacitor doesn't have a 3D design. You click here the 3D model, and you can upload your 3D model here by going to File, New 3D Model. And here you just click Add File. You upload that same file that you have downloaded, which is this one here, but it has to be in a zip format. So you just add it to a zip file. No, extract NAP. 7-zip. Add to file. I'm not seeing it. Anyway, you upload this file here, you create your own file, then you go to the 3D model and you can select it from your workspace. You can change the size, for example, instead of 18, maybe make it 22, and you adjust it to your pad, and like that you will have a 3D part for your PCB. For example, this part here wasn't needed, so I had to download and create a part for this shunt resistor. This driver, I've also created this in Blender, and then just one by one you can add it. For example, these resistors don't have a 3D design, so all you can do is just go to your PCB, select this resistor, go to 3D model, and maybe search for resistor. Okay, this is very small, but you should find one that should anyway, let's just say that we add this one, update 3D module, we save it, and now when you open the 3D view, you should see that that resistor, that exact resistor, also has a 3D model. That's how you could add a 3D model for your PCB in EasyEDA. Can I ask you a question about from PCB designing, like your project, etc.? if you have any update you would like to share about the DIY microphone. Yes, I have. Let me just take all the parts for that. As you can see, all that back there are all my projects. Some are finished, some are not. I have a lot of projects on my to-do list. Let me just change here to the OBS. A lot of projects on my to-do list, and each of those boxes are filled with components that I need for a project. So for example, as you can see, it says HQ microphone, so high quality microphone. I have all the components here. I've made a lot of tests, and I'm designing the 3D design to merge with this mesh, because this will be the noise insulation part. I have the sound card, which by the way, this is very good, but I will buy a new one because I found a better one and also cheaper. So usually I make a lot of tests. When I have but those tests are okay, I make a prototype, usually on this kind of PCBs. This is a prototyping PCB. By the way, you can get this design from my shop on Electronoobs.io, and just download it and send it to PCBWay.com, and you could have the same design. And like this, because it's black, it doesn't have any margins, because usually when you buy such a PCB from AliExpress, for example, prototype PCB, as you can see, they have these margins here, and I don't like that. That's why I designed my own. You can just buy it from here, download the file, and for just $5 you can order this at PCBWay if you want it. So let me just change to only webcam. So as you can see, I have all the parts in this box, and once I finish with all the tests, I start making the 3D design. I'm still working on that design, and at the same time I'm working at different other projects. But till I'm not sure that this project will work, I won't start recording it, because as you can see, I have to make a video each week. So if I start a project which I'm not sure about, and by the end of the week that project won't work, I have to start over once again with a different project, and like that I will lose a week. So basically, in between the projects that I record, I make tests with all those projects there. I make the tests, the prototype, the 3D design, the final design, and then I record it. I make a script, record it, record a voice, edit it, and post it. So there is a lot of work. So if you have any project that I once tell you that I will do and is not ready yet, that's why, because I have to make a lot of tests till everything is okay. So stay tuned, because I will have the project with the microphone ready soon. I think maybe the next month I will start printing the final design and making the project. Okay. If you have any other question, I think my cat is hungry. I can hear it. Okay, guys. So basically, that's how we can design. Bro, my question. Sorry, I didn't see it. Where is your question? How can I customize the board outline? Like not the regular shape. I've already showed that. I've shown you how to customize the board outline. I just talked about that like 10 minutes ago. How do people generate the DFX file? Sorry, I haven't seen that question. But are you talking about DXF files for EasyEDA or other software? Because for EasyEDA, all you have is to go to fabrication and download the Gerber files, and these are the files that you send to your PCB manufacturer. If you want just the vector file, you can just export it as a PNG file or SVG or this DXF file. So maybe you can open this in Photoshop and edit it, but usually I use PNG or SFG. And that basically here you select which layer you want to export. Let's export just the top layer, export it, and that will open a picture like this. I'm not sure if it's this what you are wondering or not, but you can have something like this in EasyEDA very, very easy. Just export it and that's it. So guys, basically, you have an idea, you test the idea. Please use prototyping boards all the time, such as this one or the other board, which right now I don't know where I placed it. Okay, place it inside of the box. Yes, I should have done that. So you have an idea, you test it on the breadboard or your prototyping PCB. You make a prototype. If the prototype works, you can pass that final schematic from drawings with your pencil to EasyEDA. It should be something like this. This will be the final schematic. Please use these kind of connections. You make the schematic, then you pass it, you go to design, convert to schematic. You select the position of each component more or less. This has to have some logic because the inputs are on the outside, the microcontrollers in the middle, the voltage regulators should be close to the input of the power, and so on. Then you decide the power, the track thickness for the power and digital signals. Sometimes I'm using, for example, this is power track of 3 millimeters, but this is also power because this is 5-volt supply, but this has only 0.8 millimeters. And then we have the digital signal, which is 0.3. So this PCB has 3 types of tracks: 3 millimeters, 0.8, and 0.3. You route all the tracks like this. Make sure that you use 45 degrees angles. Don't make the tracks too long. Be aware of the exposed copper tracks if you are working with high voltage and so on. Make the shape of the PCB as you want it by just double clicking the pad and just moving the pads around, and that will give a unique shape to your PCB. And once you have it, the final part should also be of adding a copper plane, but in this case, since it's working with high voltage, I don't want to do that. But if you want, just click this button here, select what kind of plane you want to add. In this case, I will add the ground plane. Just select the area like this, and as you can see, that will automatically add a copper plane. And we can do the same for the bottom part. Ground once again, select the area, and as you can see, that will add a copper plane. But I don't want that because the clearance for this is at least 4 millimeters, and as you can see, if you add a copper plane, the clearance is very, very small. So just remove that, or maybe just add a copper plane here on the digital part, something like this. And as you can see, you still have a clearance between the high voltage and the low voltage, but you have a copper plane on the digital part. You can do that as you want. And once you have the Gerbers, the final PCB, you can just run the design rule check, which is the DRC. And as you can see, we have no errors. And in case that you have an error, let's just, for example, let's just merge this track with the top one. As you can see, we have an error. Let's just say that you have that error. It will have here an error clearance. You click it and it will take you to that error. You just solve it, save it once again, run the design rule check, and as you can see, if you have no errors, you can just go fabrication, Gerbers, download the Gerbers. You go to PCBWay.com or any other manufacturer if you want, GLC PCB or any other. Quote now, give the size, I think it was 70 by 30. I only want 5 PCBs. This will be 2 layers. It will be this kind of material of plastic. Let's just make them black. Calculate, add your shipping, you save to cart, and on this page you just upload the Gerber files that you have just downloaded, which are this one here. You submit the order and that's it. It will be approved and you can order it. Let me just remove this because I don't want it. And just like that, you will have your PCB to your home. So if you have any final question before we finish this live stream, you can just place it now. It can be related with PCB design or my channel in general, but don't worry, I will make another Q&A soon in a live stream. And also, as I told you, I will make a mailbag video because I just received a new product, and usually I received like maybe 10 of these bags or boxes each week. So it will be very interesting to make a mailbag and show you what kind of projects or parts I receive for my projects and talk a little bit about that. I think that will be very interesting. So tell me if you have any other question. Okay. Should we fill the rest of the PCB with copper? That depends on the project. I've just told you a few moments ago that, for example, if you're working with an antenna on top of your PCB, it's not that good sometimes to add a copper plane because that will create more noise or even create some sort of capacitor with the antenna. Just have in mind that a PCB has two layers. So if you have the antenna on the top layer and you have a ground layer below, that will act as a capacitor because between the copper track of the antenna and the copper track of the plane below, you have a separator, which is an insulator, and that will create a capacitor. So have in mind for what purpose you want to add that copper plane. Usually I add copper planes for all my PCBs, for normal PCBs, for example, the multimeter. The multimeter is this one here. And as you can see, I have a copper plane. Is filled with copper, because in this case I don't I think I tried to make some changes for this PCB, but anyway, in this case I don't care about high frequency signals or radio signals, so I add a copper plane just to be sure that I will have ground all around and so on, and also remove some noise from the voltage readings. So it's your decision depending on the PCB that you are designing. I've learned a lot, thanks for sharing. I'm very glad that you have learned something new. Bro, can you give me some tips about how can we measure the quantity or the quality of fruits using some sensors? And can you name some sort of sensors? Well, if you want to measure the quantity, it's very easy. If you want to measure the quality, that depends. I think the quality is given not just by color, but also by touch, by weight. So that's a very difficult project. I think the first thing that occurs to me is to use an AI with a Raspberry Pi and a camera and just record the color or the spots on your fruits, like strawberries or apples, and you can detect the color, and by that you can sort them, like this is a good fruit because it's all red, or this is a bad fruit because it's not red yet, it's only green, and you can separate that. But of course, the quality of a fruit is not given only by the color. You have a lot of, you can weight them, you can measure the size, maybe with some IR sensor that can measure the size between 2 points. As you can see, someone says, Ace Deep, try using color sensor, for example. But even better than a color sensor is just use a camera and just implement an algorithm in Raspberry Pi to detect type of colors. Why not LED-free PCBs? Well, when you shop for PCBs, it's your decision on what you want to order. For example, the price will change. So if you don't have too much money, you will go with the basic one, which is just a plastic fiberglass in between and just a normal copper HLSS with LED, because that's the cheapest one. If you change it to LED free, let's just calculate. Oh, it's still €5. I didn't know that. I think if you merge it in gold, it will be 46, but LED free is $8. So you can select with LED or LED free. That's your decision. I didn't even knew that the LED free has the same price as the other one. And for example, if you want the base of the PCB, which is basically the material in between, to be aluminum, and actually I'm not sure if you have seen in my cart that I will be ordering a PCB that is made with aluminum. I'm not sure if I can see it, which is this one here, because I'm making a laser power meter. So basically I will have an aluminum plate with a heater on top. I will place that on top of a Peltier module, and this, as you can see, it has a lot of tracks. This will get hot, and I will calculate the power that this is wasting, and since it's aluminum, it will transfer that power into the Peltier module and pass that power into heat, and like that you can measure the power of heat that is generated. And at the same time you will have a laser pointing at this Peltier module, will be colored in black, and it will absorb that power, the light power, and transform it into heat. And just by comparing the power that you are putting into the resistor and the power of the laser, you can measure the power of the laser. So I think that will be a very interesting project. Stay tuned for that. So you can, that's why I wanted to tell you that you could also select the base of the PCB to be aluminum, but as you can see, it will be a little bit more expensive. Instead of just $5, it will be $30. So depending on what you are selecting, for example, if you're working with very low resistances and very high frequency signals, you might want to use hard gold for your pads or immersion gold. But as you can see, that will increase the price up to 40 volts. $40. I'm obsessed with volts. Sorry for that. Okay, what more we have here? Hey, I just joined the stream. Hello there for anyone who just joined the stream. By the way, I'm not sure if I told you, but if you make a post with Electronoobs, you might appear in my live streams, but it has to be on Twitter. Okay. How do you choose on which side of the PCB to lay the traces and the vias? What? That depends. For me it's not important. What is important is for me is the track thickness and to reach the point where I want to go. So for example, if I want to go from here to here, I will make the track as short as possible, and each time that I have to change to the other side, I will change just to pass some sort of other tracks that I have in the way. So if you want to make a PCB for only one layer, because it's a lot cheaper, you can do that, but usually 2 layers is just $5. So it's your decision where to place the tracks. The idea is to get from this point to the other point with the track, the least amount of work and the least amount of the length for the track. So basically that's how you, in my case, I select on which side of the PCB to lay the tracks. Okay guys, so I think that we will be ending this live stream here because it's been like 2 hours. I hope that you have learned something new. If so, consider commenting below, and I'm very glad if you have learned something new. Have in mind that I will be making a lot of more live streams, because right now YouTube is promoting the live streams and the shorts a lot more. So if you have any question, I will post this video as a video or a normal video on my channel. So leave those questions below. So like that, I could prepare for the future update of this series. We will be designing PCBs. I know that we haven't talked too much about this PCB, but don't worry, because on Sunday we'll have a full tutorial about this one, and I'm very excited because this is dangerous, this is powerful, this is big, and this is awesome. So I hope that you like this project. And I haven't seen any other project like this one on YouTube. I mean, there are some projects that are using the same driver, but they are using a transformer at the output, but this project is not using a transformer. As you can see, this one has the high voltage creation, then we have the driver, the IGBTs, the coil, and the filtering capacitor at the output, and this will be creating a full sine wave inverter, a full sine wave at the output without any kind of transformer, and up to 500 watts, and actually this could go up to 3000 watts if you add more of these transformers, because this transformers is the part that is limiting the power. So stay tuned for that. So as I told you, leave all the questions below, and I will see you in the next live stream. Thank you very much, and have a wonderful day and weekend. Keep up, you guys. Bye bye.